Welcome to Lesson 6, Multiple Representations of Linear Functions. In Lesson 5, we saw 4 different linear functions. In each case, we began with a concrete model or a real-life situation. Then we derived an equation. This equation was algebraic. It contained symbols such as x's and y's, which are the variables, numbers or constants. We had pluses and minus and equal signs. These are all symbols. They pertain to the language of algebra. Then we derived a table, a numerical table of input-output values, pairs of numbers that were instances of values that satisfied the algebraic equation. Finally, we took those pairs of numbers, plotted them in the Cartesian plane, the xy plane, and we saw the graph. The graph was not solely those 5 or 6 points that we plotted, but it was the line that joined them to include all the infinite number of points that were all lined up. In theory, the graph was the entire line, but when we have a real-life situation, usually we're in the positive x values. In this lesson, we are going to work with the different forms of representation more clearly, more precisely. These forms of representations are often referred to as follows. When we talk about the story from which the function comes, it's called the verbal representation or the situational representation. When we then have the algebraic equation, we will either call that the algebraic representation or the symbolic representation. Then we have the table of values. That's often called the numerical representation because it has lists of numbers in columns. It's also referred to as the tabular representation. Tabular from table. And the final one that lies in the geometric plane is the graphical representation. We're going to look at the interconnectedness of the 3 latter representations, meaning the equation, which contains algebraic symbols, the numbers, which are found in the input-output table, and the graph in the geometric plane. Algebra is notoriously symbolic, and very often those symbols and that symbol manipulation is very abstract and distant from students, especially in an introductory algebra course. Now, with the advent of mathematics technology and graphing calculators and computers, we are able to have a greater and deeper meaning of those symbols and constants that lie in the equation. And that is possible through the power of visualization. Let us begin by revisiting the last 2 linear relationships that we saw in Lesson 5, the last 2 linear functions. They were y equals 25x plus 45, which was Reed's reasonable rates, the electrician who came out to fix your problem at your home, and y equals negative 18x plus 250, the interest-free loan, that payment plan, that reimbursement payment plan you had with a good friend of yours, to whom you owed $250. For the first function, we saw that the table of numerical values, the input-output pairs of numbers, was as follows. 0 to 45. That meant if the electrician worked 0 hours, you still paid him $45 for the home visit. After 1 hour of work, the bill would have been $70. After 2 hours, $95. All the way down to after 4 hours, $145. Of course, if the problem took more than 4 hours to fix, the number is not on the chart. Those pairs of numbers were translated into the plane, and we get the points 0, 45, 1, 70, all the way down to 4 and 145. These ordered pairs are then plotted, and they constitute the graph of the function. In fact, they're only part of the graph, as we said, because the electrician could take 2.5 hours to fix the problem, or 3.25, or 1 in 20 minutes, 1 hour and 20 minutes. So we really do need every single point on that line from 0 to theoretically plus infinity. I'd like now to go to our mathematics technology to take this first equation of the two we're going to analyze today, the Reed's reasonable rates, and see how we analyze the graph, what it looks like, and what information this visual representation can give us. In the first list, L1, I would like to key in the x values, or the input values, which in this case are the number of hours the electrician will work. L1 will be 0, then 1, then 2, 3, and 4. That's how many we had on our input-output table. In the L2 column, we will key in the amount of money it will cost for this many hours of work. So $45 for the home visit, $70 for the first hour, $95 for the second, $120 for the third, $145 for 4 hours of work. We now can plot these points. This is in the statistical mode, so we need to go to stat plot. We have L1 and L2 now full of numbers, so we want to plot L1 versus L2. We need to turn it on. So by highlighting on, we've turned it on. We now go to zoom. In number 9, we will revisit this very often, zoom statistics. We select that, and there are our points in the plane. If we were to trace to see what we have, this first point that is on the vertical axis, or the output axis, says that when x is 0, y would be 45. The next one, x is 1. There you go right here. Y will be 70. X is 2, y is 95. X is 3, y is 120. And when x is 4, y is 145. Here are the points from our table. But we were saying earlier that we could have a 30-minute job, or we could have an hour and a half of work, or we could have 2 hours and 45 minutes. So what would we pay the electrician if the amount of time that he worked would be between one of these integer values, 1, 2, 3, 4 hours? In order to do that, we need to graph the continuous line that connects these points. This is a discrete graph. We need the continuous graph. So let's go to the y equals menu and key in the function 25x plus 45. And now let's graph the two together. And now we see that the graph, in fact, extends infinitely to the right of 4 and to the left of 0. Because in theory, this function, 25x plus 45, exists everywhere. This part of the function in quadrant 1 applies to our story, because negative hours wouldn't make sense. Now, if we wanted to trace this, notice if I put trace, I still go from point to point, but I want to be able to trace every single point along the way. So we need to turn off our stat plot, meaning these discrete values. So we go to stat plot, plot off is number 4, we select it, it is now done, and when we graph the function, we have all possible points starting from 0 to plus infinity. Let's trace and see what we have now. The spider always comes up somewhere in the middle of the screen. This says that if the electrician worked 2 hours, you would have to pay him $95. But now watch, if I do something like 2.30 or 2.5, this is about 2.5 hours, right? 2.5 hours. Then you would have the value here, which you would find on the vertical axis, which would be $107. And that's a price that would be between 2 hours and 3 hours. Let's also look at another nice feature that the calculator has, and that is the table. Let's go to table set. And to set the table, we want to see the values from the choice your choice for the minimum value. Let's start at 0, since that's the minimum amount of hours that he would work. In other functions, you might start with another minimum or initial value. And the increment of 1 means that between each hour, the calculator will jump a whole unit. If we now go to table, here we go. We have here the hours, 0 all the way down as far as you want. Of course, we hope you wouldn't be at your house for 14 hours, then you really have a bad problem. And then in the right column, you have the corresponding cost or fee that you would that he would charge you. If we go back to this table feature and change to the increment, we would still start at 0, but we would change the increment to 0.5. That means that you would see the price change for every half hour. Let's see that table. So now you have 0, half hour, 1, an hour and a half, 2 hours, 2.5. You can change that increment to anything you want. You could change it to 0.33, which would be a third of an hour or 20 minutes. And again, the corresponding cost here, and you see when we get to half hours, we get into 50 cents here, $107.50. Wanted to point out another thing about this table. When we originally had the input values, we put them into the lists, the L1 and 2 lists. Now that we have a function in the Y menu, when we go to the table, we have them under the X and the Y1. Notice again, the function is under Y1, so the table shows Y1. If I had keyed in the function under Y2, you would have the Y2. So, both the tabular representation and the graphical representation can be provided by the graphing calculator. We are now able to look more carefully at this table you just saw that will come up on the next visual, because I want to look at it a little better. We see that the change between 0 and 1 in the X column or input column is 1. The corresponding change in the Y column is 25. Also between 1 and 2, our change is 1, and again between 70 and 95, the change is 25. And so on, down to the change between 3 and 4 is 1, and the change between 120 and 145 is 25. For each change of 1 unit in the input column, which is a change of 1 hour, there is a corresponding change of 25 units in the Y column, which is $25. That means that for each additional hour of work that the electrician will work at your house, he will charge you an additional $25. His hourly rate stays the same. It doesn't change. It is constant. This ratio of the change in the output value divided by the change in the input value is called the rate of change of the function. Let us see how this rate of change translates into the graph. Let's look at the graph a little more carefully also. We see that from 0 to 1, we have a horizontal distance of 1 unit from left to right. Then when we go up to the next point, we have a vertical move or vertical distance upward of 25 units. Again, from the second point to the third point, we cover a horizontal distance of 1 unit, and then we go up to the third point and we go upward by 25 units, and so on until the last point. We have between 3 and 4 a horizontal change or move of 1 unit from left to right, and upward to the last point 25 units. Each rightward move along the x-axis or the input axis or the horizontal axis of 1 unit corresponds in this case to an upward movement of 25 units along the vertical axis or the y-axis or the output axis. This is an opportune time to talk about slope. We've already called it rate of change, but we have a very specific word when we talk about lines, and that's slope. You have an intuitive idea of what the slope means, because we use the word slope for a hill or the side of a mountain. There are other words also, such as incline. We talk about the incline of some railroad tracks or the incline of a road. We talk about the steepness or the slant or the gradient. There are a lot of words in English that talk about, at what angle the surface is with respect to the horizontal. Well, in mathematics, we measure the slope of the line, of any line, numerically. In order to do that, we take any 2 points of the line, and the slope equals the ratio of that change in the output value divided by the change in the input value, which is the same thing as the change in y over the change in x. For this reason, we call slope also, equivalently, we call it rate of change, because it's the ratio of 2 quantities that are changing. If x1, y1, and x2, y2 are 2 points on the line, the slope, which I'm calling a in parentheses right now, we'll see why we call it a later, is the quotient of y2 minus y1 divided by x2 minus x1. Equivalently, if we use the function notation, which I'd like you to get used to, the slope equals f of x2 minus f of x1 divided by x2 minus x1. If we wish to quantify the slope of this particular line, we could take, for example, the first 2 points, 0, 45, and 1, 70. Then the slope would be the change in y is 70 minus 45 divided by the change in x, 1 minus 0. That gives us 25 divided by 1, or 25. Now, for those of you who might be a little skeptical, we could take any 2 points and you could try a number of pairs of points. Say we take the second and the 5th point. Then our slope would come out to be the change in y is 145 minus 70. The change in x is 4 minus 1. The numerator gives 75, the denominator 3, and that quotient is still 25. Whichever pair of points you would pick, the slope would be the same. That is, if it is a line, because if it's another type of function that we will visit later, that rate of change changes. In this case, the rate of change or the slope, remember those are synonymous, remains the same. So when we look at this numerically, we have a number 25. When we look at it verbally, we say slope or rate of change. What about graphically? How do we see this constant change? Well, I like to refer to it as the staircase effect. Look at the next diagram. If you imagine for a moment a staircase along which you would place a flat sheet of plywood, this diagram illustrates a longitudinal section of the staircase with the sheet of wood lying upon it. If all stairs are equal in size, the plywood would touch the edge of each stair. Each edge would be a point on the line. The run of the stair, which is the depth of the stair, would be the change in x, and the rise of the stair would be the change in y. In this case, we would have rise over run. And in some algebra books, interestingly enough, you find as a definition for the slope of a line, rise over run. Perhaps they got it from a staircase. The reason I don't use rise over run is because it indicates falsely that there's always going to be a rise, whereas sometimes a line will fall, like the next example. So I prefer to say change in y over change in x. Y could change by increasing, or y could change by decreasing. So now we've come full circle back to the equation. Y equals 25x plus 45. Notice that the slope is the numerical coefficient of x. 25x is called the linear term. And there is another value, and that is 45, that along with the slope determines the line uniquely. And I think we saw that this value 45 is the output value that corresponds to the input value of 0. So 0, 45 can be found in the table. Likewise, on the graph, we find the point 0, 45 at the intersection of the line with the vertical axis. For that reason, we call it the y-intercept. So we've traveled full circle. We started with a story. Then we derived an equation. Then we computed some numbers and made a table, input-output table. Then we plotted these points and made a graph. Then we came back, looked at the equation, and hopefully have a better understanding of the meaning of 25 and 45, which are the two key numbers or constants in this particular equation. Now let's go back to the second equation, our interest-free loan. The equation that describes this situation we saw was y equals negative 18x plus 250. And the corresponding input-output table of ordered pairs x, y is indicated by the next visual. We have the graph we also saw was a line, this time moving downward. As we follow the line downward, starting from the point 0 to 150, which says that if I make 0 payments, I owe the full amount of 250. When I go to the next point, 1 to 132, in this case means after I make 1 payment, I still owe 232, all the way down up until my y values become 0. I cross the horizontal axis, I have paid off my debt. Let us look now at the graphing calculator. This time, I have already keyed in the values because there are so many. In the first case, we did it together. So here you have the payments, 1, 2, all the way down to 14 and 13. And in the L column, or L4 rather, I have the original balance of 250, the amount I owe after 1 payment, 2 payments, 3 payments. Let's look down here, something interesting. We already saw that, but let's say it again. After 13 payments, I still owe, or you still owe, $16. In fact, your monthly payments were 18. So if you make a payment of 18, this means you have overpaid by $2. That just means that that last payment will have to be changed to $16 rather than $18. And when you look at all sorts of payment plans, when you buy a car or a house, very often there's an adjustment made to that last payment. Let us plot these points by turning on Stat Plot. Going down to 2, we want to turn on L3 and L4. Now it's on. We go to Zoom. Zoom 9 is Zoom Stat. And there are the multiple points from 0 to 150 up until your balance becomes 0. The overpayment is indicated by the fact that we're below the horizontal axis. If I now go to the y equals menu and I key in negative 18x plus 250, I can graph the line and it joins all those points. If we want to delete those lines and look at the continuous graph, meaning from the points, which is a discrete graph, to the line, which is the continuous graph, I just turn off my plots. That's 4. I push enter. Now it's done. I now can graph the continuous graph. Again, before 0 and below the horizontal axis does not apply to this problem, but in theory, this line exists everywhere, so it extends to plus infinity and to minus infinity. Let's visit our table. Set the table to 0 before you make any payment, and 1 would be your increments of 1 payment at a time. We look at our table, and there we have them. These are our payment numbers, and these are the corresponding balances. In this case, let's make one more comment when we go back to the graph. You might say, well, we don't need the continuous one because we really have to make integer payments, whole payments of $18. Yes or no? Let's say 1 month you don't have the $18, you might make a half a payment of $9, then this graph would help you find your balance after any amount of money that you would pay back. Once again, our tabular representation or numerical representation and our graphical representation can be found on the graphing calculator, can be done and performed on the graphing calculator. If we look at our table of input-output values more specifically, we see that the change between 0 and 1, our first payment is a 1, and the corresponding change is negative 18 between 250 and 232. The next one, we have a change of 1 in the input column between 1 and 2, and the corresponding change of negative 18 in the Y column. And so on and so forth, all the way down to the last one between 13 and 14. The 13th and 14th payment of 1 is a change of negative 18 between $16 and negative 2. Again, we have the same staircase effect if we were to zoom in anywhere along the graph. The only difference is here that as I change a horizontal change or a move on the x-axis of +1, I come down on the y-axis or vertical axis of 18. So it's a downward falling staircase. If we wish to calculate the slope of this line, we can take any 2 points. If they are consecutive, the slope would be negative 18 over 1, which is negative 18. But if you'd like to check and make sure, take any 2 points. For example, the point 1, 232 and the point 13, 16. Between those 2 points, the change in y is 16 minus 232 divided by 13 minus 1, which gives us a quotient of negative 216 divided by 12, which is again, luckily, negative 18. We have come full circle back to the algebraic or symbolic equation of y equals negative 18x plus 250, which is the equation of the loan repayment plan. Like in the previous case, we have negative 18 is the numerical coefficient of the x term or the linear term. That is the slope or the rate of change. The other important constant or value that determines this equation uniquely is the 250. In the table of input-output values, we found 250 to be the corresponding output value for that very important input value of 0. That translates into the graph as that unique point where the line intersects the vertical axis, where the line intersects the output axis. And for that reason, we call that point the y-intercept. Well, I hope that these multiple representations of functions have helped you visualize, understand, give more meaning to what a line or an equation means. In the past, if we had only explored the symbols, y equals negative 18 plus 250, without a story that goes along with it, or without a table of input-output values that goes along with it, or without a graph to show how the values are decreasing, it would have been more abstract, perhaps a bit more challenging, a little different. But today, in today's world, when we have all these different ways that we can convey the same idea, we can travel back and forth among these four different forms of representation. And I challenge you to do that, to go back and forth. In one of the following chapters, not next one, but the one after, we're going to do just that. We'll go from one form to the other and back. But for now, I'd like in your mind to clearly see that we have at least 4 different forms of representation of linear functions.